Your fellow classmates. That is hilarious. That's not going to make your grade go up, Rory. That's the best part of the video right there. No, there. Stop it. Okay. All right, guys. Anybody have anything else to confess to? No? Any questions from stuff? Have you guys tried any of the stuff out in chapter 15? Like some of you guys are like this. All right. I kind of came ready for questions, but I mean, if nobody has questions, we'll just yes.
15:1, number 6.
See 15:1. You said 26?
6.
6. Number 6. What are you? Oh, you're this thing. Sorry, I just wanted this thing. It was falling off. Oh yeah, this is the one I was telling you about. Okay. Stay here. Go away. Stop. So this is similar to stuff you saw back in Calc 1. This is the one you're talking about, right?
Yeah.
Yes. So we got a 20-foot by 30-foot swimming pool filled with water. Depth is measured at 5-foot intervals, starting at one corner of the pool. Blah blah blah. Estimate the volume of water in the pool. So the idea is these are like the little regions in our XY plane, and the number inside is what? The depth, yes? You guys with me? Mm-hmm. So can't you get the volume of the rectangular solid that this represents? I mean, do you guys understand how that represents a rectangular solid? How? How what's this dimension? Well, how wide is it?
5.
And how long is it? 5. And how tall is it? 2. Yeah, so every one of those is a little rectangular solid. So could you get the volumes of each of those? And then to estimate the volume in the pool itself, you would just add them all up. Yeah.
Can you just shorthand that? We don't want to see all the work for that data.
I mean, there's a lot of repeats in there, yes?
Yeah.
So if I were you, I would at the very least say 1, 2, 3, 4, 5, 6, 7, 8, 8, 2. So you could do 8 times that volume plus. You guys, you with me?
Yeah.
Yeah, dear God. You don't have to do
5 times 5 times 2 plus 5 times 5 times 2 plus 5 times 2.
Is that cool? So yeah, you could shorthand it. You could at least tell me what the hell you're doing to get to the number you get. Is that cool? That is a piss poor pathetic example of what we do in real life when we take observations. We don't have a function. We don't want to model our data with a function necessarily. If all I need is an estimate of, in this case, the volume, I don't have to model what I get. I can just get a decent estimate from what the observations I took. And of course, just looking at the numbers, can you visualize this pool? Where does it seem to be the deepest? 25 feet over and 10 feet.
Yeah.
That one, yes, yes. So it's kind of a niftily shaped pool. There's a little deep portion of it towards one side. Okay. All right. Good question. That's what I had in mind when I told you you could do some of these without calculus. This is just like, you saw something like this in 180. Okay. Anything else? So that's a good question. If nobody asked that question, I get concerned. But did that make sense what I said?
Yeah.
Beautiful. Yes. It's loading? Okay. Question loading. Student's face with a little spinny thing on it. That's the awesome Wi-Fi that we have.
Okay, it's 15.2, question 12.
Oh, there we go. Alright, so this guy here.
But it's not like there that you want to find.
Yeah, but do you think this is roughly what that is?
Yeah, I think so.
Okay. Does anyone notice something, why isn't this as nice as it could be? What's another way I could say that? What part of this tells you you're gonna have to be a little bit careful? That's another way I could say that. What do you wish was here?
Just number.
Just a number, that would be amazing, because then we have a rectangular thing, it doesn't matter which way you set it up, yes? Okay. Unfortunately, we don't have just a number, that we have a function yet. So what's probably a good first step?
Define x, y, define dx, dy.
Mm-mm. Oh, I see what you mean. Figure out which way it goes?
Yeah.
Okay. Sorry. And what do you do before you can figure that out? Sketch the region, yes. So almost always the first thing you want to do with these is sketch the region they're talking about. Because then it's just easier to kind of like scan to see which dx, dy, and what one does while the other one does. So, okay. Did anyone try number 12 and have trouble, or have you tried doing that? Or who asked that? I'm sorry. Roar, you asked that.
Yes.
Did you try sketching the region they're talking about?
Yes.
Okay. And to be really honest, do you guys see that this is defined already for what X is doing? If I wanted, you should always sketch the region. You really should. But do you see they're already telling me Y is going from 1 to 2? And X is going from Y minus 1 to 1? Can anybody tell me what the internal integral should be? Which D what? The internal integral. dx. Because X is the one that's going between something of the variable limit. Yes? That should be the inner one. Stop for a minute.
The inner integral should be dx.
So on this specific one, I could just set it up and see if that works. And the 2x plus y function inside is really nice. So it should almost not matter which way it goes. But if I'm you, I'm going to get some practice sketching these regions out. Is that I don't know if that's really helping any, Rory. Do you understand how...
And it looks like they said the inside function was y, but not x.
Okay, let's see.
Wait, if it's like 2x plus y, would that mean it's in x? Or no, 2 plus y.
2 plus y, what do you mean?
It's like, they said 2 plus y dy and then dx. So that means that dy is the inside function, right?
Where did they say that?
It's not the same problem.
Oh, I'm sorry. Okay.
Just on my problem.
So yours says 2 plus y, dA? And what are the limits for yours? Can you see it?
It looks like negative 1/5 to 1/5.
Neato. And that's what y is doing?
That's what x is doing.
X is doing. Okay, and what's y doing?
25x squared to 1.
Okay, gotcha. So basically everything I'm saying now will apply to you because they've already got, all right, let's do this. Can everybody take a minute, try to graph that D there. Everything we're gonna do, Rory, should apply to you. You ask me to throw away paper somewhere? Sort of, okay. Let me just do this here. So this D right here. You guys think you have it drawn? You guys? Okay. Oh, good. The room filled up a little bit. Good. A little concerned. All right, I'm going to show you what I got. I got that. So as y goes from 1 to 2, yes, as y goes from 1 to 2, x, sorry, get out of there, x. I love myself, I do. Oh, did I look at that backwards? I kind of did. As y goes from 1 to 2, so if I pick a y, x goes, they have this order, I just put an x there. X goes from this wall to this wall, and that would be, this wall is y minus 1, and this wall is x equals 1. This is x equals y minus 1, and this is x equals 1. So real quick, let me redraw this. Okay. So it tells me y goes from 1 to 2, yes? Let me zoom out a little bit. Y goes from 1 to 2. That part I can start with, no worries. For any given y in there, x must start at y minus 1. Okay, so how do I graph y minus 1? What's the lowest y can be in this problem? No, what's the lowest that y can be? No, what's the lowest y can be? 1, because it told me. It's one of the first things it told me, yeah? When y is 1, what is x? 0. Good. So when y is 1, x is 0. When y is 2, x is 1. So that's how I got that one. So as y goes from 1 to 2, pick some arbitrary y, x goes from this wall to that wall. How do I draw this wall? X equals 1, yes. It's a vertical line. I love it. So this is the region that we're talking about. Yes? So if I wanted to change the limits, I could now, because I've got the little picture. I don't think I need to. So for this specific problem, did I need to draw the region? Not really. Watch what I mean. If I let the outer one be dy, yes? Y is going from 1 to 2. What is x going from to? Y minus 1 to 1. And then my inside function is 2x plus 1. I'm sorry, 2x plus 1. Is that okay? Now yours, it's got different stuff, but it works the exact same way, just with what they told you. Does that make any sense? So, I mean, I could have made this function here anything I wanted to, and I would have just put it here. So this problem, it's already telling you what y is going from to, what x is going from to. You still should try to draw the region just to get practice with it. And even if the problem did that, maybe there's a reason I would want to switch the limits, and it is very difficult to switch the limits of integration if you don't have the region drawn to look at. So very quickly, just for fun, how would I switch the limits of integration? If I made this dx on the outside. So then x is going from what to what? 0 to 1. So pick an arbitrary x. What is y going from to? Yeah, it's going from y equals 1
to x plus 1.
Good. If, wait a minute, let me think about it. Where'd it go? There it is. If x is y minus 1, y is x plus 1. Kabam. 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 Is that okay? I mean, that's the kind of manipulation you have to be able to do. Very difficult to do if you don't have the drawing. How do you guys feel about what we just did? Okay, all right. Especially if you haven't tried many of these out, then you're not going to know how to feel because you haven't had experiences to know how to feel about it. Okay. Anything else from homework stuff? Is William here? William shares? No, okay. And nothing else from homework? What's happening on Monday? Quiz on what? 14-7? 15-1, 15-2, I like it. You would, Jeff. When's the test?
April 30th.
30th. I like it. Okay, good.
You said 14,
So I moved it back a day, just because I wanted to. Because
Can you say the units again for the quiz?
yeah. So quiz Monday. Will be 14.7 through 15.2. So it'll be finding the maximum, finding critical points, doing the D thing and all that kind of business. Yes. And then 15.1 was the basics of rectangular regions. 15.2 was actually setting up integrals over those regions, general regions in the XY plane. Sort of like what we just did. Okay. If there's no questions from homework, number one, I'm concerned. Number two, we're just gonna get back into where we left off. Last thing we did, we kind of reviewed polar coordinates. Did we? Let me see. Did I even bring a copy of that sheet with me? Probably not. Okay. By the way, real quick. My life has been dominated. Somehow I'm going to give back my linear algebra students. You're going to get your test back tonight. Holy shit. I'm 2 away from being done grading those. I got 2 more people to grade. Those of you who aren't in my class, you're all like, I don't give a shit about this. I'm sorry. But it's been sort of dominating my life. So, yeah. I think we definitely, this is old news. But the last thing we did was the polar coordinate review, which I, of course, didn't really bring a copy of it with me. Did we essentially finish? I'm pretty sure we essentially finished that. I talked as much as I wanted to about the main points. There were a couple we didn't do, but it's up to you if you want to look at them and ask me questions. Hopefully it kind of came back. If you think you've never done that before, that's an issue. That's sort of like if you're in this class, like, what do you mean sine? You mean like a stop sign? See, that's the same level of concern I would have. So hopefully you've done some polar stuff before. If not, 15.3 is really going to be a trip. So let's do this. I still have to finish the derivation of what the integral is going to look like. So in general, if I'm trying to do the integral of a function of x and y, and this, it really is just the next natural step. From Calc 1, I have a little sliver of the x-axis, that's dx, and then I got my function hovering over that. Now I've got dx dy, so I have a little area in my xy plane, and I've got a function hovering over that, correct? So that dA, if it really is x and y, the dA would be potentially dx dy, yes? Holy shit, that's a little mutant y. He said, oh, I'm just gonna let him be. No, I can't do that. You're like, what letter is that, Jeff? I don't know. Okay. You guys with me? And of course we talked about sometimes you might want to make it dy dx, blah, 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 blah. Okay. So now we have to talk about, and I sort of got us almost there last time. What does that dA element become in polar? That's really the whole game. So the basic idea of a double integral dealing with a surface over an input plane. Did everything I just said make sense? Shit. Bless you.
Thank you.
So the main idea with a function of 2 variables, yes, is that I have an input plane, bless you, and I've got the outputs over that. Or underneath it, yes, but that just means that I get negative outputs. You guys kind of with me? So I'm just going to say over it just because it's even. and that's what we all are. So if I change my coordinate system, which just means instead of using xy, I could use r theta. And of course, you're going to start to learn, after we talk about this, we're going to talk about what polar coordinates could look like in 3 dimensions. What's the 3-dimensional analog to polar? For xy, it's xyz. Ooh. Yeah, a big rectangle, yes? A big rectangular solid. For polar, there's actually, 2 options we're going to talk about, but that's going to come into play later. So the idea of a double integral is independent from the coordinates you use, but the expression for dA is completely dependent. So it's going to be a double integral function dA. Depending on what coordinate system I'm in, dA is going to be different. When I do triple integrals, it could be dV, because now I'm talking about potentially going across a volume, yes? In which case, for xyz, it'd be dx, dy, dz. Is that cool? If I have a big ass box, and like, what's the volume of the box? It's 2 times 3 times 4, whatever, the length times width times height, yes? But if it's a big old circle, and I'm in what's called spherical coordinates, then that's going to be different. Okay. Let me bring it down, I'm sorry. Just want to talk a little bit about where we're headed. So it's really nice when it's x and y, because that's what we've been playing with the most for our academic life, yes? When we go to r theta, that's relatively new. So the things I want to remind you about were, if I'm given a circle and I want to know the arc length, what was the formula for that? Does anyone remember?
R theta.
R theta. And if I want to know the area,
1/2 r.
I love it. So we talked about those 2 things last time. Now, remember very quickly, remember how I'd have like a type, whatever the shit this was, type 2 I think they called it, in x and y, yes? All that kind of business. And we talked about one or the other is going to be dy dx or dx dy. In polar, what I'm going to have, to be very general, is I'm going to have, how do I want to draw this? Well, let me see. Let me be nice to start off with. It doesn't really matter. So I'm going to have these kind of like, so this would be a function, r equals some function of theta. This would be some r equals some other function of theta. And this would be the region over which I'm doing stuff, yes? So I'm not going to, so if I do a little tiny piece of this, I have to talk about its dimensions to figure out its area. Because that's the whole point of this game is, what do I put here? If it's in the xy plane, easy as shit. X times y. So dx, dy for a little element, yes? So I need to know what's the area of that piece going to be. So let's do this. Let's blow this thing up. See, which way do I want to go with this? Yeah, okay. So let me kind of blow this thing up a little bit. Okay, so that's blown up a little bit. Yeah, okay, so, can somebody tell me if I move further out, what am I changing? The radius. So do you see how this would be dr? Is that cool? Sort of like if I have a little element in the xy plane, and I say, what's this? You guys would say that's dx. Yes? Okay. Now, as I move like this, what's that going to be? D theta. But I want to know how long this is. So d theta is sweeping. It's not a length, though. Yes? If you're like, unless you're Han Solo, you're not going to describe a length in terms of degrees or something. Yes? I don't know, the other parsecs and stuff. You don't get that. Can somebody tell me what the length of this is going to be here? So let me ask you this. At this point, I am at some radius out. Yes? Okay. I like it. I'm trying to make a decision on the fly here as to which way I want to do this. Yeah, sure. Okay. So I'm at some radius out to this little element. So then, what is the actual length of this? Good. So this length is actually r d theta. The smaller this gets, and by the way, this is kind of a very, very large compared to the units, the kind of notation I'm using. This is way too big. Because what does this notation really mean? Infinitesimally small. So the smaller I make this, what's this thing going to become more?
Straight.
It's going to become straighter, yes? So in the limit that this goes to 0, doesn't get to 0. But in the limit that goes to 0, all the sides are straight. So therefore, what shape would it be?
Square.
Rectangle. Don't know if it's a square because the sides are, I don't know if they're the same length. So what is the area of this little element then? R, dr, d theta. Is that cool? So it's one extra little piece on top. It's not if it's rectangular, dx, dy. All the sense in the world. Yay. If it's r theta, it can't be just dr d theta because d theta is not a length. How does that make an area then? It can't. So the actual length of that side is r d theta.
Why not just dr?
What do you mean? Sorry.
Why is it not just dr d theta? But why do we multiply it by r?
Again, how, so if I do this by big steps, so let's say I go out 7. If I go out 1 more, then this length is 1, yes? If I rotate by a certain angle, this length is not equal to that. Because that would mean this length is the same as this length is the same as this length. Yes, because they all have the same angle, don't they? So if I want to know area, I've got to multiply length by length, not length by how much did you turn. Are you with me? Okay. Do y'all agree that if you're a little bug on a record player, number 1, that's trippy. But number 2, the further you are away from the center, the more you actually move over time. You are moving the same angle. So if you're here, you move by this much physical length. If you're here, you move by that much physical length. Isn't that bigger? But don't you go through the same angle? Okay, I think I beat this poor little thing to death. So you guys get that. I need an actual area. So I need a length. Well, this is an actual length, isn't it? It's a difference in radii. That is a length. The other side, I can't just say d theta, that's not a length. That's how much it turned by, but what is the actual length that far out is r d theta. Okay, how we doing? I desperately want you to see, desperately, I am so desperate, that in general, I'm just going to put an F in there. There. That is the most general idea I could use. How many coordinate systems are there?
As many as you guys.
Yeah, basically. There's an insane number of coordinate systems. I know 7 basic ones, and each of those have like 5 different variations based on what situation you're in. And we're going to see this. So, would you rather integrate x squared plus y squared, or would you rather integrate r squared? I mean, especially if, what's another? So you're going to see, there's one of the first examples we'll do. It's really, really crazy with xy, but it becomes stupid easy when I go to polar. So why in the world do we have so many different coordinate systems? Because each one has its own set of problems that are easier to do with those coordinates. Each one of them we completely made up. We just made shit up. So we're like, hey, there's a whole other way to make this shit up. Really? Yeah, there is. You can just do this. And then mathematically, some of them work better with certain problems than other ones. Okay. This idea carries through. If I have something, I don't know what it's defined, what coordinates it's based on, but I want to integrate over a region under that function, I might go negative, but dA. And that dA element for x and y was either dx dy or dy dx. That dA element for polar is going to be r dr d theta. Yes?
So is that R a constant that we can just sort of pull out?
No, it's not a constant.
Okay.
It's trippy. It's one reason why we almost always integrate with respect to r first, because there's an r built in already.
I guess it would change.
So if my f was r, I'll end up with r squared inside. Do you see that? And I can't pull it out because the inner integral is based on r. Okay. Do you always have to do it this order? No. Will you almost always do it in this order? Yes. Because r is normally the one that's defined as a function of theta, and theta is normally the one going from like pi over 3 to pi over 4. So that's normally going to be the outer interval. It's the one based on constants. How we doing? Yeah, like we don't know yet, man. Let's try a problem. Yes.
So the outside integral would be like some
Angles.
radian, like
Yes. Yes. As you sweep from this angle to this angle, your r goes from here to there.
Okay.
Yes? So if you look back at my original picture, as I sweep from this angle to this angle, my r goes from this wall to that wall. So you can still look at it as walls, yes? It's just that my entire coordinate system has now been like, you take the x, y, and you kind of connect to make circles, and then you got the polar coordinates. It's kind of crazy. So of course, polar is going to be trippier because we're not as used to it. Well, let's do an example to kind of see if we can buy into this a little bit. So what about this? What if I want to... Some of the problems are going to start with x, y stuff. So let's say I've got this function. Which one? This one. And I want to integrate this. I want to find the volume under this over a region D in the xy plane, where x squared plus y squared is less than or equal to 2, and y is less than or equal to x. Now, this is not always true, but when you see x squared plus y squared, you go, well, I'll try this with xy, but polar would probably be easier. First thing I want you guys to do, what is the first thing you should do? Draw the region. Yeah, so in the xy plane, draw the region that describes. Be careful. I don't know where I get this problem from, but we'll do it. So like y less than or equal to x. How do you draw that?
You shade
Shade what? From where?
below the
Below what?
line of
Beautiful. Thank you, Roy. Roy's like, what do you want from me? Beautiful. So you graph y equals x because it's allowed to equal that. You don't have to make it a dotted line. And then you shade below it, yes. But it's also got to be in that what? What's this guy? Circle. Now, of course, Jeff, being so nice, made it a circle of radius root 2, yes.
Thanks, Jeff.
Okay. So as you're drawing this, you start to realize something else you should do. What should I do algebraically? Figure out where these two things. Yeah, because that's going to be where it's containing. Yes. So roughly, I know I'm going to have a circle of square root of 2 radius, and I'm going to have this, and so it's going to be there. That's not good enough, though, right? I need some more detail here. So if I knew where those two things intersected, I would know what these were, and I can go from there, yeah? Now, some of you guys might realize, what angle does this define? If I drew this better, great. 45-degree angle. Yes?
Can you explain it again?
Which part? Sorry.
Like, why are we getting less or equal to?
No. This is given to us.
Oh.
Sorry. So this is the whole problem. I want you to, in order for me to ask you a problem related to what we're doing, I have to give you a function, and I have to give you what it exists over. Sort of like it would be really mean for me to say, I want you to find the definite interval of x squared, and then I don't tell you where. Okay, good. So I have to tell you where the inputs are coming from. Yeah. Yes?
So in these situations, we would use all 4 quadrants, not just like the one, like when we were looking at the graphs earlier.
There was an example we did earlier where it told us I was in the first quadrant somehow. I can't remember. So that's why we focused on that. It was, go ahead.
We've just been doing a lot of them in the first quadrants.
Yeah, I'm sorry. If that was true, I didn't realize. It could be anywhere. Literally, the little region that we're talking about could be anywhere. It could be a little circle region way down here. Okay. So I've got to be inside this circle and below this line. I know this defines a 45-degree angle. Is that cool?
Mm-hmm.
Okay. And this is a circle of radius 2. But let's see. What's another way to do this algebraically to find that point of intersection? Well, it's not. Yeah. Why is it that and not that? Because it's not a radius. It's 1. It's a radius rad 2. So, all right. Let me show you the algebra. The intersection between these two would be where y equals x. So if I just rewrite this and replace x with y with x, yes, so I get x equals 1. And if x is 1, what's y got to be? 1. So that makes sense because it was supposed to be on the line y equals x. Yes?
Root 2 over 2 times root 2, so you get 2 over 2. If you do it the other way,
Yes.
it becomes just
There you
sine
go.
over y.
If you do it the other way, you have to be careful about the fact you don't have a unit circle.
Yeah.
Okay. This is the algebraic way to do it.
Yeah.
Bless you. So if x is 1, y is 1. So I'm at that point. Okay. And of course, what's going over here? Of course, I kind of left out plus or minus. It's kind of important. So it should be, where do I want to say this? Oh, why am I doing an inequality? I'm trying to see where these meet. Plus or minus 1. So then, of course, down here, this will be -1, -1. This will be 1, 1. Okay. So if I try to do this with rectangular coordinates, how do you define this? Do you see how you immediately run into a problem? Because I can define the top half of a circle, I can define the bottom half of a circle. Right there, I'd have to break it up. I need you to see what I'm talking about. If this is true, for this, couldn't I define solve for y, then the positive one would be the top half of the circle, yes? And the negative one would be the bottom half of the circle. But the region I'm working with uses a little bit of the top half and a little bit of the bottom half. So immediately, I'm like, I don't know, because that's 2 integrals I need then, yes? Because the definition of one of my walls changes at that point, right there.
You're trying to find the area?
Huh?
Are you trying to find the area?
No. What am I trying to find? Volume. So I'm this region is in the XY plane, and above this is this surface. I'm trying to find the volume between the two. That's a really good question, Rory, because it gets really confusing. Two-dimensional drawing, much easier than three-dimensional drawing. Almost always, you only have to focus on the 2D part. And you know that this thing is kind of like above this. So if I wanted to know how far above it was for any point, I would just plug that in and see what I get, right? Okay. Can somebody tell me, all right, side note, where's the guy have the highest height? Isn't this really 1 over this squared? Yes. So the way to make the output the biggest is to make the bottom the smallest, and when x and y are both 0, so at 0, it is up 1. It's right there. Yes? Okay, yes. Oh, you're good. So if I try, do you guys see how I automatically do not want to try to set this up with rectangular coordinates? What is it about the problem that by itself tells me polar might be a good option? X squared plus y squared. Yes? Okay. So if I want to try to make this into polar, the first thing is, what does my f function become?
R theta.
Yes, f of r theta.
R squared plus theta squared.
R squared plus 1 to the negative 2. Yes? So I'm converting everything to polar now. Yes? Now here's where the angles are going to come into play. This is where it's really good to look at it from an angular standpoint, because now I need dr d theta kind of stuff going on. Yes? So almost always it's going to be r dr d theta. Can somebody tell me what theta is going from to? You could? Yeah, yeah. Yes, negative 3 pi over 4. I stopped pi over 4 short of 180, right, of pi. So it's negative 3/4 pi, yes? Negative 3/4 pi.
To 1/4 pi.
So 1/4 pi. Kick ass. And then, what is r doing? Yes, this is nice. We know this already. You know this from the beginning. What's r? What's the biggest r could be?
2. Squared.
1.
What's the radius of the circle it lives in?
So
Root 2. So r goes from 0
squared
to root 2. In fact, what does this become in polar?
R squared.
So isn't r between, if you want to be really pedantic, you could do this, but we normally don't include negative r's because we can just rotate to get to negative r, yes? Okay, maybe. The more you've done polar, the better that's going to be. So r is going to go from 0 out to root 2. So think about it this way. I look at an angle, and then I let r go from this to that. That's 0 to rad 2. Then I look at the next angle and I let r go from this to that, then this to that, then this to that. And as I change my angle, scan. Change my angle, scan. So I'm standing at the origin, and I pick an angle, and I let r go from me to rad 2. And I kind of like accumulate whatever that is. And then I rotate just a little bit. And then I go out again from 0 to rad 2. So you can still look at this as from this wall to that wall.
And then if you want to do it the other way, it's like scanning each angle, kind of.
That's why we almost never do it that way, for a couple reasons. Normally theta is the one that's got the constants, and you want that one to be the outer one. And almost always r is the one that's functional.
Yeah.
So, and then inside I'm just going to put r squared plus 1 to negative 2. So this goes from, like we said, 0 to rad 2. How could you integrate that? Ask ChatGPT. No. Huh? It's just USO, right? Now, obviously, some of the problems you guys are working with are contrived to a certain degree. That little R dude that's a part of the DA piece is going to save your ass. In this case, it saves your ass. If it wasn't there, you'd have to do, well, to be honest, it wouldn't be that bad if you know the, yeah. But you can see how, in general, it could get kind of rough. Yeah.
Does it save my ass because it's a circle in this case?
No, because then it links you sub work. Do you see that? Yes? If I just incorporate that R? So it's a little trippy. I understand. And I love the question somebody asked a minute ago. It was a perfect question. I expect that kind of question. The R is a part of the DA piece, but the minute you start to write the interval, you just suck that sucker in. Now it's a part of the stuff inside. It is a legitimate little R dude. He has to be considered. So somebody had a question about, can you just put layout R outside? No, it's R. It has to be integrated. Yes?
Does the R, D data come from the R-plane formula?
Totally. That's the whole thing we did earlier about trying to figure out what DA was when I'm in polar. RD theta is a length this way. DR is a length this way. So to get the area of that piece, I multiply those two. Okay.
How to change limits of integration from DR D data to D data DR?
Do you want to?
Is there going to be any time where we need to?
All right. You can tell it would be very difficult.
Yeah.
But the nice thing is, it's very rarely anywhere near anything you need to do. Now, I appreciate your question because your question kicks ass. I don't care if I need to. I just want to know how. In this problem, there's no connection between theta and R.
Yeah.
So, and to be really honest, let me see, how can I say this? Since these are both, neither one of these are based on a function, you could literally, this is an example of like a rectangle in XY. I could switch the limits. Will these always be just constants here? No. In that case, then that's where that question would come into play. Then you have a relationship between R and theta.
Mm-hmm.
Like before we had a relationship between X and Y. Then I could try to consider how to convert those, but you don't want to. Okay. So how do I, so this should be very quick. Yes? Let U equal what? R squared plus 1 du is 2R dr. 2R dr. So I need a 2 here, so I put a 1/2 here. So then I get 1/2 and a roll. You guys see that? No. I'm going to assume you all have this written down.
Yeah.
And a roll. Negative 2R dr is du. And R squared plus 1 is u. Oh, did I lose I lost my interval. What do these limits become?
0, 2, 2.
Yeah, because when R is 0, be careful, when R is 0, I get 1. And when R is rad 2, I get 3. Kick ass. You guys see that? R goes from 0 to rad 2. U is R squared plus 1. When R is 0, U is 1. When R is rad 2 squared is 2 plus 1, U is 3. Let me stop for a minute. Again, it's really unfortunate that you guys don't have enough time. I'm going to say something very strange. And you're like, yeah, we're used to it. You don't have enough time to marinate in an idea like polar coordinates. It just comes up every now and again. And I'm like, oh yeah, I've seen that stuff before, that weird shit. So this probably is trippy for you. I don't know. You're not used to polar coordinates. So I understand that part. But once we got the integral set up, it doesn't matter what they are. They're just variables. I can do all my old by parts, u sub, whatever the hell. They're just variables. They work exactly like any other variable would. The trippy part is setting up the integral. Once I got it set up, it doesn't matter that's r. I don't care that's r. It's the derivative of the bottom piece, so blah, 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 blah. I can use u sub. Sorry. Blah, 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 blah. Is that helpful? Did you write that down? So how do I integrate that?
You change it to u -2.
Sure, u negative 2. And then how do you integrate that?
Add 1 to the power,
Yes?
and then divide by the power.
So you get negative u to the negative 1 from 1 to 3.
Which is 2/3.
So 1/2 integral negative 3 pi over 4, pi over 4. Yeah, that'll be negative 1/3 plus, sorry, negative, 1/3 plus 1, so that'll be 2/3. Thank you, Zach. One half of 2/3 is 1/3. Integral of 1 d theta is theta. Evaluate it between these things, and you'll get 1/3 pi over 4 minus negative 1/3 3 pi over 4 is 1/3 pi.
Wait, hold on.
Huh?
Can you run that back?
Sure. That last piece?
Last
Oh,
two
no, it makes
pieces.
sense.
Last two pieces. Okay. This will be negative 1/3 minus negative 1. So negative 1/3 plus 1. So that's 2/3. When I integrate d theta, I get theta. 1/2 of 2/3 is 1/3. When I plug in pi over 4 minus a negative, we do it like this. 1/4 pi plus 3/4 pi is a whole pi. So I get 1/3 of a pi. Now, the really sucky thing about these is there isn't necessarily a great way to tell if that answer makes sense. Sometimes in 180, if you graph it, it's close to like something you know the geometric formula for. You could actually estimate if that answer makes sense. This one, not so much. Okay. Let's try another example out.
Where the 1/3 came from? Next to Q?
That's not
Oh.
a pi.
Are you cool with the 1/2?
Yeah.
Are you cool with the 2/3? What's 1/2 of 2/3?
I see.
So I just pulled that out. Yeah. Okay. All right. Let's see. Whoa. Oh, I guess I'll pick some out of the homework. Yeah. Okay. Let's look at here. Let's do one out of here. Oh, okay. So real quick, first level question. Which one of these looks like you could use rectangular coordinates pretty well?
2 and 5.
Yeah, definitely 2 and 5 looks good because they have straight sides. That makes sense. So they work really well. Anything that is a piece of a rectangle, especially, or anything that has straight sides to it. Any region like that, I'm thinking XY coordinates. Obviously, anything that's part of a circle, more than likely, polar is going to be better. Is that always true? Of course not. Almost nothing is always true. Yes, but that's the way to bet. If you're taking some weird bets. So let's do this. Let's try. It doesn't matter. Let's look at number 10 just for an example. So let me put this up here. You guys write down what you need from this. Okay. try to draw the region they're talking about. Oh yeah, this is perfect. Is this one I wanted to do? Maybe. I don't know. All my notes are jumbled. Do, 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 do. Oh, that's perfect. I have no idea if this is a homework problem, so you guys can all hope it is. Alright, let's see. I'm going to catch up to you guys. So everybody got what they need from the problem? I can take it away? Okay. I don't have it. Let's see. So, my region has got to be in the first quadrant. So they're feeding into that. Glad I didn't do this one first. Yeah. It's got to be in the first quadrant, enclosed by the circle x squared plus y squared equals 4. Holy shit, I didn't really zoom in. First quadrant. What do you know about this circle? R is 2. Oh my god, Jeff. Well, alright. Poor little circle. Had no chance. First quadrant, that circle. And the lines x equals 0 and y equals x. X equals 0 means what? Means the y-axis. And the way to remember that is, if I say x equals 0, x cannot change. I can't move left and right. I can only move up and down. Y-axis. Yes? So this is a wall. What's the other wall? Y equals x. So there's another wall. Okay. So where's my region actually? I drew a little too much of something, which is fine. It's going to be this pizza slice here, yes? So not this. Okay. So, I mean, real quick, this is why you really want to be careful about when you draw your region. Because if you draw the wrong, it's really easy to think it's going to be that lower part, and then all your limits are on. Yes? Because then you have your stuff going, the angle's got to go from the wrong place, and so and all that.
Y equals x was inside the problem?
Yes.
Okay.
Sorry.
I just found it.
Yeah. Yeah, the y-axis and y equals x. Okay. So if they would have said y equals 0 and y equals x, that would have been this bottom slice. Yeah. So let's put some stuff in here. This is x squared plus y squared equals 4. So if I'm looking at my integral, where'd it go? There it is. Now, the problem is telling me to switch to polar. Yes? You can kind of see why, because you'd have to solve that equation for x or y based on which way you want to do dy dx. If you're going to do rectangular, it could potentially be a little gross. This is not a great example of a problem that's really obvious that you should do it in polar, but why are we going to do it in polar? Because the problem told me to, damn it. Okay. Yes?
This one has 3 constraints.
Mhm.
Right, so whenever we kind of see 3 constraints, it would make sense to check if it can be done in polar.
No, careful, no. If the 3 constraints are part of a circular function,
Okay.
then it could be polar.
Yeah.
And it could be polar even beyond that, to be honest. But when is it going to be more obviously polar? When at least one of my walls is some kind of circular function.
Oh, right, because usually we would just do 2 integrals. Okay.
Yeah, okay. So obviously, what does this become?
R squared equals 4.
So that becomes r equals 2. We normally don't do plus or minus because to get to negative I can instead just rotate.
The other one.
So instead of telling somebody to walk backwards, just tell them to go 180 degrees. Yes? Okay. How do I determine, alright. So I need to figure out what my theta is doing, and I already can see what my R is doing. Let's start with R. What is my R doing? Oh, I gotta change this too, wait a minute. Let's start with this. Let's start with this. Okay. What does this become? What is X in polar? R cosine theta, thank you. And what's Y? R sine theta, good. There we go. Now I can write all that business, and now we can focus on the limits. R is kind of easier to start with, because what is R doing? As I pick an angle, just pick an angle to look at. What is R doing? 0 to 2. Thank you, R. You kick ass. So we'll do, the next example we'll do is the limits won't be nice whole numbers. I mean, the limits won't be constants, they'll be functional. And what is theta doing? How do you determine what theta is doing? Yeah, what was this line again? This was y equals x. So that one we know. It's pi over 4. And of course this would be, no, pi over 2. I cut you off, I'm sorry, Laura. You're right. Such an asshole. Okay. And then you integrate this thing. So, again, this one has no issue if you switch them, but I don't see a reason to. Yeah? So how do I integrate with respect to R? Well, the very first thing I probably should do is pull my R in, yes? This poor little dude. Pull him in there. Oops. Oh yeah, didn't have any, that's right. Okay. Does anyone, alright, it's not that big of a deal. Do you see how I could separate the R and the theta? Because I could pull that R squared out. You could remember how we wrote the integral blah 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 dr and the integral blah 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 d theta? You don't have to. But I could if I wanted to. I don't know if you guys understand what I just said. One thing I can do for myself is I can pull that R squared out of here. So then I can kind of focus on it, yes? And what is the integral of R squared? Yeah, it'll be 1/3 R cubed from 0 to 2. Do you guys start to get the feel for how this internal evaluation kind of works? When you do the first integral, you can just attack that piece with the limits. That becomes its own little tiny problem. Everything else is just sitting there waiting, just looking at their watch going, all right. So this part's just going to wait. So then I get another piece of paper. Pi over 4 to pi over 2. When I plug a 2 in, I get 8. So I get 8/3. When I plug a 0 in, I don't get shit. And then, of course, that's not going to be too bad. I'm going to pull the 8/3 out. Get out of here. What's the integral of this? I don't need that sign anymore. What's the integral? That's a negative. There we go. 2 sine. Plus cosine. Good. That changing gears thing, right? Pi over 4, pi over 2. And then you get, when you plug a pi over 2 in, that's 1, that's 0, so you get 2. And when you plug a pi over 4 in, you get rad 2 over 2 times 2 is rad 2, rad 2 over 2, and that should be a minus because I'm doing that right now. Okay. So then you get whatever the hell that is. What is it? It's going to be 8/3. -2 rad 2, -3 rad 2 over 2. It'll be 2 rad 2 minus 3 rad 2. No, 2. It'll be 4 minus 3 rad 2 over 2. Blah, blah. If I want to do it that way. And then I could, like, do more stuff, but it doesn't matter. Alright, so the last part doesn't matter. That's easy enough. What matters is the middle part. So normally, I think you've already picked up on this, the hardest part about these problems is setting it up. And especially with polar coordinates, you could get to a point where graphing some of the regions gets a little trippy because you're just not used to it. So let me try to find one with a slightly more interesting thing happening. Let me see, did I do any with... Oh, here we go. All right, let's try this. Let's see. Oh boy. Yeah. All right. Look at 20. Should I do 18? Maybe something not too trippy. Does 18 do what I want it to? It sort of does, yeah. All right, yeah, let's do 18. Okay, 18's not too evil. So that is the kind of spiral, r equals square root of theta. As theta gets bigger, r gets bigger, correct? Does that make sense? As I rotate, so at 0 degrees, what's r? 0. So then when I get to pi over 2, r is the square root of that, and it just continues to get bigger, yes? Obviously, the restriction is I can't go this way, because I got a square root to handle negative inputs, yes? Okay. It's a very trippy looking picture. So we need to figure out that area. Now, if I'm trying to find the area of this, and this is all right, I'm trying to find the area of this, correct? What function, f of r theta, what am I going to put into my double integral? What do I want my height to be to get the area? What? That's an example. It's one of the very first things I did is to show you guys how Math 180 problems become Math 281 problems if I consider a height of 1. Yes? If I find the volume under 1 over this region, that actually is a 180 problem. Okay. Do you guys understand? Did you do, well, actually some of you guys did. But if I do double integrals, this kind of area is much easier to find. Even though it isn't truly a three-dimensional thing, a double integral makes this area much easier to work with. So, it all boils down to then what my limits are going to be. In this case, what does it look like theta is going from to? 0 to 2 pi. Kick ass, bless you. And obviously, if it went past 2 pi, it gets a little bit trippy because then some of our area is overlapping area that's already there. So we sort of try to stay away from that. So are you with me so far? Okay, so this is our first example we're doing together that didn't start off as rectangular coordinates. And what is r? For any given theta, what is r doing? This is my book, so I can write it. So if I just pick an angle, so let's say this angle here, what is r going from to? 0 to square root theta. I love it. So this is our first example where the inner interval won't have just numbers. Yes? So this was nice because they already graphed the region for us, and sometimes that's a big stumbling block, understandably. Can you guys set up the double integral? What's dA going to be? R dr RT theta. Yes. So I am going to put a 1 inside but the R isn't a choice. It has to be there. The R d theta, because that's what dA is.
R goes from 0 to.
Square root of theta.
Pi. Like, when we're doing our integration, it's root 2 pi. Or do you keep it as root theta?
Oh. Do you agree with me that R, as I rotate, goes out further and further?
Right.
So it cannot go from 0 to a number, because as I rotate, it goes further. So it goes from 0 to whatever square root of theta is at that moment. Yes. You're welcome.
So it's 0.
Okay. This one, in terms of a little baby step, is not that problematic, I hope. I'm gonna put a 1 in here, so it's all about my limits. Wow. I'm doing way to shit. Very first thing we looked at was what theta does. Theta goes from 0 to 2 pi. And we just spoke about if I just pick any value of theta. This is exactly what I did with x and y. I picked an x and I saw what y did. Picked a y, saw what x. Pick a theta. Where's our start? Where does r go to? So in this case, r goes from 0. Square root of theta. I like it. Tripadelic. Your question was pretty good because, especially when we get to triple integrals, but sometimes with double integrals, students try to plug values into the theta, but theta is going. And every time theta changes, something else changes. I can't plug a number into that because then I'm saying I'm static. And then I can never scan that whole region, yes? So the first step's pretty straightforward. No? Yes? What's the integral of 1? I'm sorry, what's the integral of r?
R squared. 1/2 R squared.
Yes, 1/2 r squared from
0 to
0 to the square root of theta.
which is theta.
Yeah, which will be 1/2 theta. Is that cool?
Yeah. But when we pull the 1/2 out,
I could pull a 1/2 out if I wanted to. I just didn't want to. Yeah. Huh? Alright, let me make sure is that cool. So there's my r. It's always there. It's always there. So if I had to plug in 1 over r, that's kind of nice. Then the r dies. So, but he's always there. He always has to get involved. So the integral of r is 1/2 r squared. Plug in rad theta. Rad theta squared is theta. What's the integral of theta? Cool. So then I get,
squared.
yeah, when I square 2 pi, I get 4 pi squared divided by 4 is
I squared.
pi squared. Yeah. When I plug it 0, I get 0. That's trippy. I don't know if anybody would have guessed that. For this weird little freaking, what's coming to mind is like, well,
snail shell.
exactly, it's like a snail. I'm thinking like a baby snail or something for some reason. Because it also looks like a what do you call them? Tramp, not a tramp, a baby stroller? No? Little wheels coming down?
Carriage of some sort.
Yes, thank you. Okay. But that's what that comes out to be, is pi squared, pretty trippy. Alright. I'll leave it up to you guys. Before we get into the next section, do you want to try one more example?
Yes, please.
Okay. Here, let's do this. Yeah, this is perfect. Look at number 31, I think. I say 31? Yeah. Okay. So, what's your first step?
Geography.
So here's the problem. Did they tell us the region over which some function lives? No, not directly. But well, sort of indirectly. I keep looking at 30 for some reason. Damn it. 31. Above the disk. So they did tell us, and that's one reason why they call it D, is because sometimes it could be a disk, but that's silly because most of the time it isn't. So that's what you're going to graph, and that's easy. So the region in the XY plane is just a what? Circle of radius 1. Good. So we have that. That's easy. Yeah? But the function I want to integrate under is what? This is where you have to. No. So with the first examples we did, didn't we start with a function of what and then convert to polar coordinates? Function of x and y. Yes? So what is our function of x and y? Yes, solve for z. Yes. You guys see that? So this one is just another step up. They didn't directly give us what f of x, y was. We have to take a minute and figure out what it is. But just like in the olden days, what did f of x take the place of? Y. Now, what does f of x, y take the place of? Z. So if I need to know what the hell it is, I solve for z. All right, so let me catch up to you guys here. Oh yeah, okay. So it's above the disk, which is just a circle of radius 1. So my domain, my little region D, it's a circle of radius 1. And of course, I pretty much know I'm going to go to this, so it's r equals 1. Where'd he go? And then z equals 4 minus 2x minus y. That's my f of x, y. Okay, so there's everything I'm working with. So what's kind of funny is if I go to polar, the limits are going to be nice and easy, yes? What's theta going to do? Zero to 2 pi. And what's r going to do? 0 to 1. I can't beat that shit. Now, okay. I can't, let me see. Yeah, it did, okay. So this problem said use polar coordinates, so they want me to use polar. The f of x, y itself does not indicate polar would be good. Do you see what I mean? So it's obvious if I have x squared plus y squared. Polar's good. What about if I had a function that had a y over x in it a few times? Why would that be good to go to polar? Because what is y over x in polar? Tangent theta. So anything that kind of directly goes into a nice closed form, beautiful. So that function doesn't really scream polar to me, but obviously the region I'm integrating over screams polar. Yes? But now I have to convert my function to polar. What does this become in polar?
4 minus.
Yeah, 4 minus, you got it, Jake. 2r cosine theta minus r sine theta. So if you were taught SOHCAHTOA, I officially apologize on behalf of my profession. If you've had me before, you know I have rants. I have rants about the radical notation. I have rants about SOHCAHTOA. SOHCAHTOA soaks. If you just remember x likes cosine, cosine likes x, sine likes y, that kind of thing is extra easy now. Yes? So what is take a minute and set up the integral. Now that we're fully in polar, set up the double integral. Maybe. Have a lot. so this is not too terrible, right? This is. Don't forget your little R dude. Sometimes people sort of forget he's there. Especially if you write it the way I did. So remind me, R is going from 0 to 1. Theta is going from 0 to 2 pi. So the real idea is, if I pick an angle, let me see if you guys are with this. You'll understand that to really see this, I would have to rotate this so it's the XY, and then I could see what's over it, correct? So if I just pick a line that corresponds to an angle, that is Math 180 now. That is an axis that I can then get the area underneath the sliver of the surface that's over it. Then I move to the next little angle, and then I do it again, and I add all that shit up. That's why I like the idea of scanning. So if I pick an angle, I scan, and then I go to the next angle, scan, and then I add all that shit up together, and of course I end up with the total volume because I added up all the little cross-sectional areas. Yes? Okay, so I like the idea of these scan the region. What do you have to be careful about? What did I just say? Yeah, so bring that R through. I don't know what you're saying, but I'm almost certain you're making fun of my writing, which is valid. No? Something else? Okay. So now I just integrate. Yeah, this is not too bad. Integral of 4r? 2r squared. Integral of 2r squared.
2/3. Minus 1/3.
Yeah. Oops. And then I have to go from 0 to 1 for my r, yes? So the nice thing to remember with these is if you're about to integrate the next variable, right? You should only have that variable inside. So if you're like, oh, I got r and theta, I forgot to plug my shit in for r. Do you see what I mean? No? Yes? So if you do more of these double integrals, you'll start to see what I'm talking about. Once you're done with the inner integral, you should only be left with variables related to the outer integral. So if I plug a 1 in, all this stuff becomes really nice. I'll get 2 minus 2/3 cosine theta minus 1/3 sine theta. And if I plug on 0 in, everything goes to 0, so screw him. Okay. Yes, yes, yes. And then that integral's easy as shit, yes?
Yes.
2 theta minus 2/3 sine theta plus 1/3 cosine theta from 0 to 2 pi. 2 times 2 pi is 4 pi. Look at me go. Sine of 2 pi is 0. Cosine of 2 pi is 1. Well, I mean, cosine theta is 1. Cosine of 2 pi is 1. And then times 1/3. I'm with you. And then when you plug a 0 in, that's 0, and that is, yeah, so it'll be minus 1/3. Should be not obvious. Again, there's no way it could be obvious. Because when I drew my picture, that's not the picture of the situation. That's the picture of the floor underneath the situation, yeah? So the unfortunate thing about these problems, when you're in Math 180, you get the picture of the function, you can kind of estimate if your area seems about right. Here, you're almost, unless you use the Desmo 3D, which I highly recommend, and even then, it's kind of hard to really pick out just the part you're interested in. You might then be able to tell if your answer kind of makes sense, but even then it's not easy. Okay. Maybe? Sorry, I pulled that away. Is there something about this? Yes, sorry.
Sorry, where did you get the 0 and 2 pi for the algorithm?
Oh, all right.
Yeah.
Yeah, I need to scan this whole thing. So theta has got to go from 0 to 2 pi, and for any given thing, ours goes from 0 to, what was it, 1 in this case, right? So obviously, if I had the upper half circle in the xy plane, that would go from 0 to pi. Yeah. Okay. All right. Yeah, there's not a lot of great variety in these problems. Let me see. All right. Meh. What is this one? Oh, this is a little bit more interesting at least. Okay. All right, last one, then we'll do a little bit of the next section. Look at 27.
And this is all 15.3, right?
15.3, yeah. By the way, I don't know if you guys remember this. And real quick, let me show you something here. Let's take a little sidestep here. Let's all watch in horror as Jeff forgets his password. Let's see. I thought for sure I was going to type it in wrong. I could have still done it. What I want to show you real quick is just how to graph things in your graphing calculator in Polar. Oh shit. I'm not going to be able to do it here, am I? Excuse me, I don't know the stupid thing. Go away. Alright, damn it. Can I borrow somebody's graphing calculator? Thank you. I let a student borrow mine and I didn't get it back yet. Oh, neat. Oh. Or you want me to?
Yeah.
You don't trust me? Here, take that. I don't blame you. Excuse me, Rory. Ooh. Okay. Feel. I have to. Now, does anyone already know how to graph polar coordinates in your graphing calculator? Yes.
Set like a mode there, something.
Yes. So if we go to mode, right up here, function, parametric, polar. You with me? I'll put it back to where it was, unless you want me to just keep it. Now when you go to y equals, you're going to have an r prompt, yes? So if I put r equals sine theta, when I hit the x button, it's not going to be x now. This is my multi-purpose variable button. Now it's theta. Ooh, look at that. Ooh. Costs enough money. Might as well be able to draw a freaking theta. Okay. Now real quick, if r is sine theta, when will the r be biggest? What is sine of 0? 0. 5 or 2. So at 0, it's 0. So when I'm looking at the 0, when I'm looking at the x-axis, I'm going to go out none. As I turn, I start to go out more until I'm here and I go out the most. So it makes sense. This is going to be a circle sitting on the y-axis. So if I do this, oh, you look at your battery. You got good battery. Let's see if I graph this thing. Oh, look at that! Look at that! Look at this pool. All right, let's see. Let's do this. How do I make the? Oh shit! How do I make that a little bit bigger circle? I could zoom in, or I could put like 5 here. Ooh, look at that! Now, how would I change the function so that it's a circle on the x-axis? Holy shit. Okay, right? So there's some very, very, very basic things you're going to see. If I see something sine theta, r equals something sine theta, I know it's a circle on the y-axis, right? What gets really trippy is, what if I wanted a circle like over here?
Sine theta plus cosine.
Ooh, let's see. Let me take. Okay. One little thing is getting the radius to be what you want it to be gets a little bit worse because you're adding up these lengths. You see how it's moved over a bit? Yeah. So obviously, if you really wanted to get the formula in polar coordinates of a circle that's been shifted, you start with the rectangular equation, and then you just convert the damn thing to polar. Yes? So like, what's x minus 2 squared plus y plus 3 squared equals 1? What is that? X minus 2 squared plus y plus 3 squared equals 1. That's a circle that's been shifted where? 2 to the right, down 3. Yes? Because when it's inside with the variable, you do the opposite of what it looks like. Yes? Transformations, you gotta love them. If I just start with that, replace x with r cosine theta, y with r sine theta, blah, 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 I'll get the equation, and then it will draw the circle in the right place. You guys kind of with me? So I just wanted to show you that at least. I think that's all I wanted to play around with right now. By the way, I mean, here's where you can start doing, I don't necessarily blame you if you don't do this kind of stuff. Let me see, let me go out to 4 pi. No, Jeff. No, Jeff. There you go, Jeff. Yeah, that does what I wanted. Okay. This is where you just, I don't know if anybody is, I mean, look, yes? That's like, yeah, I know, but it's also like a really extravagant pair of scissors. It's weird. Yes? You guys at all with me? I mean, just play around with this shit. Have any of you guys ever heard of a thing called the spirograph?
Yeah.
All right, so, God,
I get to feel really old.
so back in the day, before we had Nintendos or the internet's wasn't a thing yet, I still remember the first time we had a web page. You would click on the address and you would go make lunch and you come back. Oh, it's 20% loaded, and you go somewhere else. All right, sorry. There was a thing called spirograph where you have something that would fit into a larger thing, and you put your pencil into a piece and you go, wow, wow. So when you did polar functions in whatever course you did before, I'm really hoping your teacher, I actually found a spirograph thing, an online version, where you could pick the gear size and it would kind of trace out what it would look like. And then we actually found the equation of one of the things based on the radius of the gears. So there's anyway, I'm sorry. So if you never, ever, ever just sit down and start doing weird shit like this, just changing, what if you made this 2/3 theta? Do you see what I mean? I mean, now, I understand a part of you is like, I'm not going to sit there and play with the calculator, Jeff. But by the same token, you really should. And let me see. I hope I put this back together right. Okay. Thank you, Rory. I appreciate that. I forgot to change it back. It's in polar, buddy. So, good luck. Okay. So coming back to this problem. So r equals sine theta is exactly where we think it should be. What should this be? Just out of curiosity. No. On the y-axis? Ooh, dissension in the ranks. So r equals sine theta. When theta is pi over 2, what's r? 1. So that's going to be 1. So this actually is a circle of radius 1/2. Yes. Cool. I like it. Hey, Mikey. Okay. Very quickly, just because you guys have met me before. R equals sine theta. How do I convert that into a rectangular equation? What do you wish was here? And this would become a letter right away. So if I multiply both sides by r, I'll get x squared plus y squared equals y. I'd have to pull that over, have to complete the square. I know. Half of this is negative 1/2 squared is 1/4. And so then you get, so what's the radius of this? one half. Yes? Okay, alright, I'm sorry. That's all a side note. Very, very sorry. I just ran out of paper, damn it. You're like, yeah, let's go, shut up. So, that piece doesn't bother me at first. They've already sketched out the region I'm talking about. What is my angle going from to, obviously? 0 to pi over 2. What if the other half was shaded? Pi over 2 to pi, kick ass. Yes? So we've already got that figured out. What is r going from to? So pick an angle. Pick an angle. Huh? Yes. This one's not too bad, but it's kind of like the only, one of the few examples they have like this. If I pick an angle to look at, r goes from 0 to this wall, and this wall is sine theta. Yes? Okay, I like it. So what would that interval look like then? Here's a little bit of paper I've got. The function I'm working with is x. What does that look like in polar?
R cosine.
What do I put here?
R d
Good.
r.
R d r d theta. R d r d theta. Okay. So have fun with that if you want to. We said theta was going from 0 to pi over 2, and then r is going from 0 to the wall
Sine.
sine theta. So I have no idea why. As far as me looking through real quick, they didn't really give you a ton of these that are functional definitions of limits in here, but now you just attack this thing. Yeah. What's basically the first thing you should really always make sure you do?
Times the
Don't forget this dude. Yeah. Jeff.
R
There you
squared.
go, buddy. And what's the integral of r squared?
1/3
1/3 r cubed from.
0 to sine theta.
Does anyone see where this is going?
Use of.
Oh yeah, sure. Like in calc, I always find it funny in math 280, they make it its own little section. They call it trig integrals. Sine, cube, cosine. You know, if it's even, you do this. Remember that shit? It's really just use of.
Yeah.
It doesn't really deserve its own section, but oh well. Too bad for everybody. So this becomes Jeff. 1/3 sine cubed. So I'm going to pull a 1/3 out.
Cosine.
Is that cool?
Yeah.
I'm going to plug a 0 in, of course I get 0. And then, like Zach said, how will the u sub work? So this is already here. So what would u be? So this would be du.
Sine.
That's the way I try to teach this stuff. If whatever you can put together to be a du, it kind of tells you what you should do. So u should be sine theta. Then du is cosine theta d theta. I'm doing this a little quickly, and I'm sorry, but the hardest part for most problems will be setting it up. After that, it doesn't matter that this is r and theta. Those are just letters. Who cares? You integrate it the way you always do. Where am I at? Blah, 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 blah. Oh, so then it gets,
Shouldn't you reset the limits?
yeah. So when theta is 0, sine is, sorry, u is 0. When theta is pi over 2, sine is 1. And then I'll get u cubed du.
Which is 1/12.
And I've lost all interest. Because this is easy, yes? Now, if you're in my Math 180 class, I couldn't lose all interest, but
Would be 1/12.
1/3, 1/4 u to the 4th. Yeah, it'll be 1/12. Kicking the accent. How much time? Not much, as always. How did I do that? I don't know. So, I've been sort of going back and forth about this, but I think I am going to make, unfortunately, 15.4 extra credit. I know. If any of you have taken any physics, you've actually sort of already done this. This is where we talk about density, moments of inertia. It is really nifty, but again, it's one of those optional ones that I put in here because I wanted to talk about it. But to keep on track I think we're gonna have to let it go. So I'm having a moment of silence for myself. There's some really cool shit in here, but a little more important than that is this section. This section comes back, the ideas that this kind of lays down, comes back in chapter 16. Let me say a couple things about this section. With all the paper that I don't have. They're all written on already. Damn it. Ooh, look at that. Holy shit. What is it? Nothing. Great. All right. So, 15.4, extra credit. That's what I just saw. Just want to make it all official.
Yeah.
So 15.4 is there's that's what that says apparently. 15.5, we do something that we sort of skipped in a sense geometrically. We went in Math 180. You do area in Math, and you also do volumes of revolution. In Math 281, we finally do more general volumes, but we sort of there's a step in the middle we skipped. Surface area. So I have the area of a two-dimensional object in 180. Now I have the surface area of a three-dimensional object in 281. Yes? So if I have a surface, look at that. And I want to figure out, so that is very, very trippy surface, yes? It's got some weird shit going on. And I want to know its surface area. Do you see how that's not, it's obviously not immediately like easy to think about how to do that. If I look locally at any given point sitting on this surface, same thing as if I had some function, if I look locally, isn't there a tangent line here, of course?
Yeah.
So isn't there a tangent plane here? So if I have some point in the XY, and then I look up here, if I look at a region around, I got this plane that is tangent to that surface, yes? If I can find an expression for that tangent plane's area, and that, all right, let me stop. I guess I could give you any point in that XY plane and ask you to get the tangent plane equation. We've done that before, correct? We have done that before. No, haven't you seen problems from me saying find the equation of the tangent plane, blah, 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 blah. Okay, so we've done it before. If I did that for every point under that surface, so in my XY plane, I have got this region, maybe it's like this, I don't know, where every point has an output on that surface, yes? If I get the little tangent plane element at every point above the region, the D region, right? How do I get the total surface area? I just add all those up. How many of them will there be? So adding them all up turns into a integral. Good thing we're in calculus. But does the idea make sense? If I get a way to represent the tangent plane element for any given inputs, I can then integrate it across X and Y, and I'll end up with the total surface area. I'm just adding up all the little tiny elements of area. That's how you get like the length of something. You do a little length segment and you integrate all those up and you end up with how long that thing is. Yes? So this is just the two-dimensional analog of that idea. Okay. Now, the concept is relatively easy. Some of the steps involved in what I just said could get very tricky. So next time we'll develop that idea. Yes, I'm not going to try to do anything with that right now. That's going to be kind of involved. Don't forget Monday quiz, 14.7, 15.1, 15.2. And don't forget the test was pushed back to the 30th. All right.